Hey, my name is Ericka Nunez and I'm part of the Western New England University Steel Bridge team. We are designing a very interesting and excellent bridge that will be fit perfectly in the National Wildlife Refuge. This bridge will connect both sides of the trails and will provide a safe and a pleasing passage for pedestrians, vehicles, and whoever wants to go there. So let's go to an adventure here in our laboratory in Springfield, Massachusetts.
Hello, I'm Owen Feindell and welcome to Western New England's Building of Engineering. We started the design process by first kind of figuring out what kind of overall shape we wanted. We ended up deciding on we wanted a big overhead truss over the bridge to design the truss off of the stringers. So then we had the challenge of, well, how are we going to design the stringers? Then we had to design a connection between the stringers and the truss, and then we had to design a truss. One of the first things we did to figure out what exactly we were working with is we made our force diagrams right here. We tested the forces to figure out where on the bridge was going to have the most stress, where we had to focus kind of our efforts in making sure that the bridge was going to be able to hold whatever force they put on the bridge. The next step, once we generally knew where the forces were going to be, we built a generic stringer truss setup, figured out the general trusses, and then we plugged the specific members of those truss into the program F tool, and then kind of played around with it in there to make sure that our truss was ideally built as possible in order to best hold the forces in all of the different forms that they had the possibility of being in. Once we had a truss design, we could then focus on how we were going to connect the trusses, how we were going to connect the trusses to the stringers, and then how the stringers themselves were going to be together. We ended up putting the stringers together by each stringer having a little shelf that would support the next one. This would both be able to allow us to drop bolts vertically, which would hold it tighter, hold it in shear force, and just have a nice place to set the piece as we're assembling the bridge to make assembly go faster. To connect the trusses to the stringers, we fit in these little horizontal pieces in there that stuck out enough so the stringer template could properly pass through, and that could also hold the shear force as the forces were transferred from the stringers onto the truss system. Once we had that figured out, then we worked on designing the actual truss pieces. We ended up on a tubing system with little tabs on the end, a design we have used in the past, but we decided to amp it up this year. We used 1/4-inch plates, and then using the F tool that we designed before to figure out how much force was actually going to be on each of these members, we made sure that the 1/4-inch plate that was going to be used would still be strong enough to support all of those forces, even once we drilled the hole in it. So we wouldn't end up with any of our bolts shearing, any of our tabs snapping. Just wanted to make sure that all of our connections were going to be perfectly solid enough in order to support the weight that would inevitably be on the bridge.
I'm Gilbert, and I'm part of the Western New England Steel Bridge team. In order to finalize our design, we created the bridge on a 3D modeling software called SolidWorks. All the parts were digitally designed and then assembled together in a final SolidWorks assembly. This ensured that when manufactured, all the parts would fit together correctly. In order to provide professionalism to our project, we took the time to make detailed dimension drawing files for each individual part. This helped communicate our ideas and successfully transition into the fabrication phase. All of our parts were manufactured in our university's machine shop. After the steel was ordered from an outside company, we drilled, cut, and welded the material to become the final parts we designed on the software. This is where having the dimension drawings was very beneficial because it ensured our accuracy.
My name is Evan Blake. This is the Western New England Civil Engineering Lab. So we're just getting started on the construction of our bridge right now. We're getting it all tacked out, tack welded right here on the floor. We're going through making sure everything's straight right now before we do the final weld. So right now Kier's been grinding off some welds for us, and I've been going through and tacking it. And you can see this is the the final length of the entire bridge. Soon to be coming is the truss section, putting up on legs, and the final weld.
My name is Simon Bonas, and I was one of the builders on this year's steel bridge team. So how it worked was we had 6 builders total and 3 on each side. From a design perspective, we had a ground-up design with L-shaped plates, and we used much larger bolts rather than more bolts. Our bridge incorporated a unique labeling system easy for any builder to understand. The bridge is organized into 7 sections on both the left and right side. The stringers were placed in first, with the vertical and truss pieces placed second. Pieces were mirrored, and depending on label, the truss either goes in front or behind the plate, usually with horizontals in the front and diagonals behind.
Hi, I'm Kira, and I'm outside the engineering building with the finished painted members of the bridge. This bridge is going to be located in the San Diego National Wildlife Refuge. So it's very important that we consider the aesthetics of the bridge because we want this bridge to be an experience, not just crossing the river. So, paying tribute to all the engineering behind it, we wanted to make that this bridge stood out, which is why we chose to paint it a blue color scheme with accents of yellow. So to pay tribute to all of that and to the animals in this refugee center, we decided to paint a gold paw print.
Our innovative bridge would be a great addition to the National Wildlife Refuge. To ensure a professional, sophisticated bridge, we thoroughly follow the entire design process from ideation, 3D modeling, fabrication, construction, up to the final assembly. Our bridge produced promising results at the ASCE Steel Bridge competition. The bridge withstood the 2,500 pounds distribute loading with a deflection of only 1.12 inches. Our building team was able to efficiently construct the bridge in under 30 minutes, demonstrating not only our abilities in construction but also design.